40 kilograms of water every single second. That's what NASA's Swift Observatory detected streaming from a cosmic visitor nearly 3 times farther from the Sun than Earth, where water should barely be active at all. This wasn't supposed to happen. The rules of physics, the models we've trusted for centuries, the very foundations of our understanding about comets, all of it challenged by a mysterious object hurtling through our solar system at impossible speeds. What you're about to hear will change everything you thought you knew about what might be traveling between the stars. Before we dive deeper into this mystery, I need you to do something important. This story contains scientific revelations that need to reach as many people as possible. Hit that subscribe button right now and make sure notifications are on. Leave a comment telling me what you think is really happening here. Is this just an unusual comet, or could it be something far more significant? And here's why the like button matters more than you think. YouTube's algorithm determines how many people see this content based on engagement in the first few hours. Every like helps spread this information to others searching for answers. Now, let's uncover what's really happening. The object has a designation that sounds more like a classified military code than a celestial body, 3I/Atlas. The I stands for interstellar, the third confirmed visitor from beyond our solar system. But unlike its predecessors, this one arrived with characteristics that made astronomers around the world stop what they were doing and stare at their instruments in disbelief. It wasn't just passing through. It was performing in ways that defied every prediction, breaking rules we didn't even know existed. Dennis Bodewitz and his team at Auburn University spent over 2 hours stacking ultraviolet exposures, layering image upon image to capture something so faint it should have been invisible. What they found was published in the Astrophysical journal Letters on September 30th, and the implications rippled through the scientific community like shockwaves. This wasn't just unusual data. This was evidence of something that shouldn't exist according to our current understanding of how comets behave. At 2.9 astronomical units from the Sun, nearly 3 times Earth's distance, water molecules should barely be escaping from a comet's surface. The temperature there hovers around levels where ice remains frozen, dormant, waiting for the intense heat of a closer solar approach. Yet 3I/Atlas was hemorrhaging water at rates that would be impressive even at perihelion, that critical point where a comet makes its closest approach to the Sun. The numbers didn't just fail to match predictions. They shattered them completely. Think about what 40 kilograms per second actually means. That's 88 pounds of water vapor escaping into space every single heartbeat. Over the course of a day, this object was losing thousands of tons of material. Not at the scorching distances where comets typically become active, but in the cold depths of the outer solar system where everything should be frozen solid. The energy required for this level of activity simply wasn't available from solar heating alone. Something else had to be happening. The team detected something called the hydroxyl signature, a telltale glow left behind when sunlight tears water molecules apart. Hydroxyl groups are like fingerprints, impossible to fake, impossible to misinterpret. They confirmed beyond any doubt that water was present and actively sublimating. But the mass loss rate they calculated defied every distance-based prediction model we had. Comets at that range typically show 3 to 5% surface activity. 3I/Atlas was demonstrating at least 8%, nearly double what physics suggested should be possible. Here's where the mystery deepens into something truly strange. The mathematics simply didn't work for pure surface sublimation. Even when researchers accounted for every possible variable, solar heating efficiency, surface composition, rotation rates that might expose fresh ice, the energy input at 2.9 astronomical units remained insufficient to explain 40 kilograms of water per second escaping from a nucleus estimated between 5 and 6 kilometers across. The numbers had a gap, and that gap demanded an explanation that didn't fit conventional comet science. Near-infrared observations from Gemini South and NASA's Infrared Telescope facility provided a clue that transformed confusion into astonishment. They detected ice debris floating in the coma itself, not just water vapor escaping from the surface. Actual chunks of ice were suspended in the clouds surrounding the nucleus, floating free in space like a scattered field of frozen shrapnel. Once these fragments became exposed to sunlight, even the weak sunlight available at that distance, something remarkable happened. These ice chunks heated up faster than surface ice because of their geometry. A small fragment has a much higher surface area relative to its volume than a large solid body. That means sunlight can warm it more efficiently, penetrating and sublimating the ice from multiple angles simultaneously. Each fragment essentially became a miniature steam vent, hundreds or thousands of them scattered throughout the coma, all contributing to the total water output. The result created an optical illusion that made the nucleus appear far more active than it actually was. Zhi Xing, the lead author of the study, summarized it with elegant simplicity. Every interstellar comet so far has been a complete surprise. The first one, Oumuamua, arrived bone dry with no detectable water signature. The second, Borisov, turned out to be extraordinarily rich in carbon monoxide. And now Atlas was releasing water at distances and rates we never expected. Each visitor from beyond our solar system was systematically rewriting our assumptions about what comets from other star systems should look like. But this observation raised questions far more profound than it answered. Why were those ice chunks floating in the coma in the first place? Did 3I/Atlas experience some kind of fragmentation event before we detected it, shattering part of its structure and leaving debris scattered in its wake? Could this damage be the result of millions of years of micrometeorite impacts during an interstellar journey that beggars imagination? Or perhaps most intriguingly, is this simply how comets from the thick disk of our galaxy naturally behave? Their internal structure fundamentally different because they formed under conditions our solar system never experienced? The timing of these observations added another layer of complexity to an already bewildering situation. 3I/Atlas faded from Swift Observatory's view in August, moving too close to the Sun for safe observation by that particular instrument. But by early October, the European Space Agency's Mars orbiters managed to capture it during a relatively close flyby at 30 million kilometers. The coma was clearly visible, spanning several thousand kilometers across, proving that the water activity hadn't been a temporary anomaly. The comet was still actively losing material as it continued its approach toward perihelion. That word, approach, became critical, because at the very moment scientists were trying to understand what they'd already observed, 3I/Atlas was entering a period that would hide it from every telescope on Earth. Solar conjunction, the astronomical term for when an object passes behind the Sun from our perspective, was imminent. Earth and the comet would soon be on opposite sides of our star, with 93 million miles of blazing plasma and radiation, creating an impenetrable barrier to observation. The comet would reach perihelion on October 29th at 1.36 astronomical units, just inside Mars's orbit, completely hidden from our view during the most intense period of its entire journey through our solar system. The solar radiation at that distance would be orders of magnitude stronger than what Swift had detected back in July and August. If 40 kilograms per second was the baseline at 3 astronomical units, what would happen when the comet experienced 10 times that radiation intensity? The textbook answer seems straightforward enough. The comet should brighten dramatically as increased sublimation released more dust and gas into space. The coma should expand into a massive cloud millions of kilometers across. Supervolatile ices, substances like carbon dioxide and carbon monoxide that sublimate at even lower temperatures than water, should explode from the nucleus in spectacular fashion. The tail should grow into a magnificent streamer extending millions of kilometers behind the comet, swept back by solar radiation pressure and the solar wind. Scientists have observed this pattern hundreds of times with solar system comets. The perihelion passage is typically the grand finale, the moment when a comet puts on its most spectacular display before beginning its long journey back to the outer solar system. Every prediction model, every simulation, every historical precedent suggested that 3I/Atlas should follow this well-established pattern. But here's the problem that kept astronomers awake at night. 3I/Atlas had already demonstrated it doesn't follow textbook predictions. The water activity at 2.9 astronomical units wasn't supposed to happen according to our models. The 8% active surface coverage exceeded predictions by nearly double. The icy debris field floating in the coma wasn't something anyone had anticipated or seen before. This object had already violated our expectations multiple times. So what would happen during the hidden perihelion passage when solar radiation reached its peak and we had no way to observe the results? The answer was genuinely unknown, and that uncertainty was both terrifying and exhilarating. The European Space Agency's JUICE spacecraft, Jupiter Icy Moons Explorer, would eventually have the best observational opportunity. Between November 2nd and 25th, after 3I/Atlas emerged from behind the Sun, JUICE would observe with its full suite of cameras, spectrometers, and particle sensors. The spacecraft's vantage point was unique, positioned far enough from the Sun that the comet would be clearly visible, yet close enough to capture post-perihelion activity in extraordinary detail. But there was a significant problem with this plan, one that would test the patience of every scientist and space enthusiast following this story. Data transmission. JUICE was currently using its high-gain antenna as a heat shield, protecting sensitive electronics from solar radiation. This meant the spacecraft had to rely on a slower backup antenna to send information back to Earth. The bandwidth limitation was severe. Those November observations, potentially the most important data we'd ever collect about an interstellar comet during its most active period, wouldn't be seen until February 2026. 3 months of waiting. 90 days of not knowing whether the comet survived perihelion intact, whether it fragmented under thermal stress like Shoemaker-Levy 9 did under Jupiter's tidal forces, or whether something entirely unexpected occurred during those hidden days behind the Sun. For scientists accustomed to rapid data access and real-time analysis, this delay was agonizing. For the rest of the world watching this cosmic drama unfold, it meant the story would have an intermission lasting a full quarter of a year. If you're finding this information valuable, if you're starting to realize just how significant this discovery might be, do me a favor right now. Pause and hit that like button. I know it seems like a small thing, but it genuinely matters. YouTube's algorithm uses engagement metrics to determine which videos get promoted. The more likes this video receives in the first 24 hours, the more people will see it. And this is information that deserves to be widely known. Also, drop a comment about what aspect of this mystery intrigues you most. I read every single comment, and your engagement helps create a community of curious minds exploring these questions together. Now, there's another consideration here that scientists were reluctant to discuss publicly but couldn't completely ignore. Water serves as the universal yardstick of comet science. It's the baseline measurement for assessing activity levels and inferring overall composition. When you know how much water a comet is producing, you can make educated guesses about its mass, density, and the abundance of other volatile compounds. But 3I/Atlas isn't a solar system comet following familiar patterns. It's an interstellar messenger carrying information about a planetary system that formed around a different star. That parent star system potentially formed 10 billion years ago in what astronomers call the thick disk of our galaxy. The protoplanetary disk that gave birth to this object had different temperatures than the one that created Earth and Jupiter. It had different chemical compositions, different gradients of elements from the inner regions near the star to the outer reaches where icy bodies accreted. The water we were detecting might be chemically identical to our own, hydrogen and oxygen in that same familiar H2O configuration, but the context was completely alien. The ratios of isotopes within that water, the trace elements mixed into the ice, the very structure of the ice crystals themselves. All of that carries encoded information about a star system we will never visit, around a star that might no longer exist. Swift Observatory detected hydroxyl radicals, the broken remnants of water molecules torn apart by ultraviolet radiation. But hydroxyl groups can also originate from other parent molecules, organic compounds, alcohols, complex carbon-based chemistry happening in the coma as sunlight and cosmic rays break apart larger molecules into smaller fragments. That 40 kilograms per second might be pure water vapor, or it might be a mixture of water and other volatiles that produce similar spectral signatures when broken down. Higher resolution spectroscopy would be needed to determine the truth. Longer observation windows were required. And most critically, the comet needed to survive perihelion and remain active as it began its journey back toward interstellar space. Because here's the sobering reality. 3I/Atlas is not returning. After it passes Jupiter's orbit in March 2026, it leaves our solar system forever. This represents our only chance to study a comet from the galactic thick disk, sampling a population of ancient star systems we've never encountered before. Every observation matters in a way that's difficult to overstate. Every data point is absolutely irreplaceable. There are no second chances, no opportunities for follow-up missions, no possibility of waiting for better technology in a decade or two. This is it. The water detection was just the opening act of this cosmic drama. It told us that 3I/Atlas is volatile rich, that it possesses an unusual structural composition, that it's actively outgassing at distances where comets from our own solar system remain completely dormant. But the main event was about to happen in the next month behind the sun, hidden from every telescope humanity has ever built, where the rules of cometary behavior would either be confirmed or completely shattered. And when JUICE finally obtained its observations in November, when the comet emerged into view with whatever perihelion had done to it on full display, we would know whether the water loss we'd documented was merely a preview or an actual warning. We'd see whether 3I/Atlas was simply an exceptionally active comet or something that required us to rewrite the textbooks entirely. The answer was waiting, hidden behind our star, 50 days away from revelation. But the water mystery was only one piece of a much larger puzzle. Because as scientists were analyzing these observations and publishing their findings, another voice entered the conversation, one that would transform this scientific curiosity into a global phenomenon. Professor Abraham Loeb, chair of Harvard's astronomy department and founder of the Galileo Project, was watching the same data with a very different interpretive framework. Loeb has built a controversial reputation in recent years for his willingness to consider hypotheses that most astronomers reject outright. When Oumuamua, the first detected interstellar object, displayed anomalous acceleration that couldn't be easily explained by outgassing, Loeb proposed it might be an artificial solar sail. The scientific community largely dismissed this idea, pointing to more mundane explanations involving unusual comet behavior. But Loeb persisted, arguing that we shouldn't automatically reject technological explanations simply because they seem unlikely. Now, looking at 3I/Atlas, Loeb saw patterns that troubled him, patterns that individually might mean nothing, but collectively suggested something worth investigating. He developed what he called the Loeb scale, a rating system from 0 to 10, where 0 means definitively natural and 10 means definitively technological. It's analogous to the Torino scale used for asteroid impact threats, providing a quantitative framework for assessing the likelihood of artificial origin. In mid-August, Loeb assigned 3I/Atlas a rating of 4 on his scale, suggesting low probability of technological origin, but not low enough to dismiss entirely. Then something remarkable happened. Over the next 2 weeks, as more data arrived and more anomalies accumulated, he revised that rating upward to 6. This wasn't a trivial adjustment. Each point on the Loeb scale requires quantifiable anomalies and statistical outliers that resist conventional explanation. Moving from 4 to 6 represented a fundamental shift in probability assessment, and Loeb doesn't make those changes lightly. Let me start with the trajectory analysis that keeps getting cited and simultaneously keeps getting dismissed by mainstream astronomers. The orbital mechanics team calculated that a randomly entering interstellar object has only a 0.005% probability of passing, as close as 3I/Atlas does, to Venus, Mars, and Jupiter. 5 chances in 100,000. Those are extraordinarily low odds, the kind of probability that makes statisticians sit up and take notice. Loeb and his team calculated this using standard orbital mechanics and geometric timing windows, accounting for the fact that planets move along their orbits and approach windows are therefore quite narrow. The mathematics is straightforward and not particularly controversial. An object on a retrograde hyperbolic orbit entering from the direction of Sagittarius has a tiny probability cone for each planetary encounter. You can visualize this as threading a needle, except the needle is moving, and you're throwing the thread from across the room. The combined probability of hitting all 3 cones, achieving close approaches to Venus, Mars, and Jupiter in sequence, is vanishingly small. Critics of Loeb's interpretation argue that we're cherry-picking coincidences after the fact, that if you examine enough interstellar objects, eventually one will have an unlikely trajectory just by random chance. This criticism has merit. It's true that given a large enough sample size, improbable events become inevitable. But here's the uncomfortable counterargument. We've only detected 3 interstellar visitors ever. 3 objects total in the entirety of human history. And one of those 3 just happened to thread a geometric needle that gives it access to the 3 most scientifically interesting rocky bodies in the inner solar system. The Bayesian prior for that outcome, the probability we should assign before even considering any other evidence, is extremely uncomfortable. Now add another layer to this probability analysis, the perihelion timing. October 29th, solar conjunction, Earth and 3I/Atlas positioned on opposite sides of the Sun. No ground-based observation possible during the most critical phase of the comet's journey. If you wanted to perform a propulsive maneuver, a deliberate engine burn that changes velocity and trajectory, perihelion is the optimal location to do it. You're moving fastest relative to the Sun at that point, which means every kilogram of propellant yields maximum delta V, maximum change in velocity. This is called the Oberth effect, a fundamental principle of orbital mechanics that spacecraft engineers exploit constantly. Every interplanetary mission uses Oberth maneuvers to maximize efficiency. If 3I/Atlas were actually a technological object, if it had any capability for powered flight, perihelion would be precisely when you'd want to execute major trajectory changes. And this comet reaches perihelion precisely when we cannot observe it, hidden behind the Sun's glare. Loeb calculated the delta V requirements for small probes released at perihelion to reach Earth's orbital space. The numbers work disturbingly well. A modest probe, perhaps 10 kilograms in mass, using a chemical propulsion system with specific impulse around 300 seconds, technology well within current human capability, could perform a reverse Oberth maneuver and insert itself into a stable orbit around Earth. The arrival window would be late November to early December, right when 3I/Atlas emerges from behind the Sun and we start conducting post-perihelion observations. Is this actually the plan? Is there even a plan? Or are we simply seeing patterns in randomness because humans are pattern-seeking machines and Loeb has essentially primed us to look for exactly these patterns. This question cuts to the heart of the scientific method and our ability to remain objective when analyzing extraordinary claims. The size discrepancy created another puzzle that remains unresolved. Early brightness measurements suggested a nucleus 20 kilometers across if the albedo, the reflectivity, was typical for rocky asteroids. 20 kilometers is absurdly, almost impossibly large for an interstellar object. Oumuamua was merely a few hundred meters long. Borisov measured under a kilometer. A 20-kilometer comet showing up in our solar system from interstellar space would represent a statistical nightmare, the kind of event that should not occur within a human lifetime or perhaps within recorded history. But then Hubble Space Telescope managed to resolve the coma from the nucleus, and the size estimates dropped dramatically. 5 to 6 kilometers based on distinguishing the actual nucleus brightness from the total system brightness that includes all the surrounding dust and gas. That's still large, still unusual, but it falls within the realm of possibility for a natural object. It's not so improbable that it demands exotic explanations. Except there's a problem with this revised estimate. The early brightness measurements weren't actually wrong. They were real observations by competent astronomers using calibrated instruments. 3I/Atlas genuinely appeared brighter than it should have for a 5-kilometer comet at that distance. The brightness was measured, recorded, and confirmed by multiple independent observations. So what explains the discrepancy? Loeb suggests enhanced reflectivity. If the surface contains metallic components, if the shape happens to focus reflected light in our direction like a curved mirror, if the material properties are fundamentally different from the porous ice and dust we expect, you'd get anomalous brightness. You'd observe an object that looks bigger than it actually is. Now, this could be entirely natural. Metallic asteroids absolutely exist in our own solar system. But combined with everything else, combined with the trajectory and timing and water production anomalies, it adds weight to the probability scale. Another data point that individually means little but collectively builds a case. Then there's the dust configuration that Hubble images revealed. The photographs show maximum dust density on the sunward side of the nucleus, with heavy grains concentrated ahead of the comet in its direction of travel. These are the massive particles, too heavy for radiation pressure to push backward into a traditional tail. Standard comet outgassing should produce jets perpendicular to the surface based on local heating patterns. Those jets can point in essentially any direction depending on the rotation axis orientation and the distribution of volatile ices across the surface. But sustained sunward dust ejection, maintaining that configuration over weeks of observation, requires either a very specific rotation pole orientation that remains stable or something else. Something that continuously expels material in the direction of motion regardless of which hemisphere faces the sun at any given moment. Loeb points out this matches the expected pattern for debris ejection from high-speed transit through the interstellar medium. If 3I/Atlas has been traveling at 60 to 70 kilometers per second for millions of years, the impacts with interstellar hydrogen atoms are not trivial events. Space isn't perfectly empty. The interstellar medium contains about 1 hydrogen atom per cubic centimeter. At those velocities, each impact releases kinetic energy. Accumulate enough impacts and you start eroding the leading surface through simple ram pressure, the same way a sandblaster slowly wears away material. The dust we're observing could be impact ejecta, material continuously stripped off the forward-facing surface as the object plows through space like a ship cutting through water. That would be a completely natural explanation requiring no exotic physics and no technology. But it's also mechanically consistent with venting from internal systems, with attitude control thrusters maintaining orientation, with any number of technological processes that would produce similar observable effects. The rotation period measurement sits right in the middle of perfect ambiguity. 16.16 hours. Too slow to indicate spin-up from asymmetric outgassing jets. Too fast to be tidally locked to anything. For a rubble pile comet, a loosely consolidated mass held together by weak gravity, this rotation is stable and completely unremarkable. For a solid object, whether natural or manufactured, the rotation is equally stable and equally unremarkable. It tells us essentially nothing definitive about the object's nature. The measurement exists, it's precise, but it's interpretively useless. But the approach angle is considerably harder to dismiss as coincidence. Coming from the direction of Sagittarius means approaching from toward the galactic center, the most crowded, brightest region of the sky when viewed from Earth. Detection against that background is extraordinarily difficult. Every star, every nebula, every bright object creates visual noise that makes spotting a dim moving comet incredibly challenging. We only spotted 3I/Atlas because the Atlas survey telescopes are specifically designed to catch fast-moving objects, and even then it was nearly missed. Pre-discovery images dating back to mid-June show the object barely visible at magnitude 20, right at the detection threshold. A few weeks earlier, and we would have had no observations at all. The comet would have passed through the inner solar system completely undetected, sailed past our planets, and departed back into interstellar space without humanity ever knowing it had visited. If you were planning a reconnaissance mission to an alien solar system, approaching from the direction of the galactic center would be tactically brilliant. You arrive masked by background light, giving the inhabitants minimal advance warning. By the time detection occurs, assuming it occurs at all, you're already deep inside their planetary system with all major bodies in range. It's too late for any meaningful response or preparation. Is that what actually happened here? Did some intelligence deliberately choose this approach vector for its stealth characteristics? Or is this yet another case of retrofitting intent onto pure coincidence, seeing purpose in what's actually just random geometry? The early spectroscopic confusion adds another troubling data point. Multiple research teams reported no clear carbon-based molecules in the first weeks of observation. No obvious water signature, just reddish dust and ambiguous absorption features in the spectrum. The object looked active based on its appearance, but it didn't look cometary based on its chemistry. The spectral signature was wrong, not matching what decades of comet science had taught us to expect. Loeb argued this was potentially the smoking gun, proof that 3I/Atlas was not behaving like a natural comet should. The absence of expected volatiles in the early data seemed to support the hypothesis that this might be something other than a garden-variety icy body from another star system. But then additional observations came in from more powerful instruments with longer integration times. Suddenly water was clearly detected. Carbon dioxide became obvious, actually dominating the volatile budget. The spectral signatures started matching cometary expectations. Loeb revised his public position but noted that the initial ambiguity remains unexplained. Why did it take so long for the comet to show standard volatile signatures? Why the initial confusion among experienced spectroscopists who know how to recognize comet chemistry? One straightforward possibility is simple observational bias. The early spectra were low resolution, short exposure, taken when the comet was still quite faint. As it brightened and better instruments locked onto the target, the data quality improved dramatically. What initially looked like an absence of volatiles might have just been an absence of sufficient signal-to-noise ratio to detect them. That's the mundane answer. That's probably the correct answer. But probably is doing an enormous amount of interpretive work in that sentence. The uncertainty gap between probably natural and definitely natural is where Loeb focuses his attention. Loeb isn't actually claiming certainty that 3I/Atlas is artificial. He's claiming we should look carefully, that the probability is measurably non-zero, that the consequences of being wrong would be catastrophic for our understanding of intelligence in the universe. If we dismiss a genuine technological artifact as just another comet because comets are common and artifacts are supposedly impossible, we will have failed at the most important scientific test humanity has ever faced. He's advocated for the Galileo Project observatories to conduct continuous monitoring during November and December, specifically looking for secondary evidence. If 3I/Atlas does release probes, if those probes enter Earth's atmosphere or orbital space to study our planet up close, there might be a detectable uptick in unidentified aerial phenomena. Objects moving in ways that defy conventional aerodynamics. Radar returns that don't match natural meteors or human technology. Optical signatures that resist easy explanation. Is this likely? Absolutely not. Loeb himself admits the odds still favor a natural comet by a substantial margin. But the odds aren't 100%. And in that gap between highly probable and absolutely certain, we find the entire justification for the field of technosignature research. We've spent 60 years listening for radio signals from alien civilizations. We've built massive optical telescopes to catch laser flashes from distant stars. We've analyzed millions of stellar spectra looking for atmospheric biosignatures on exoplanets. But we've never seriously considered that artifacts might come to us. That interstellar objects, these very things we've only started detecting in the last 8 years, might occasionally include probes alongside rocks and ice balls. 3I/Atlas is the test case, the object forcing us to develop methods for distinguishing natural from artificial at interstellar distances. And those methods simply don't exist yet in any robust form. We have brightness curves, spectroscopy, and trajectory analysis, but we don't have a validated framework for confidently stating, this is definitely natural, or this requires further investigation under the assumption of possible artificiality. Loeb is attempting to build that framework in real time using 3I/Atlas as the calibration target. It's a high-stakes experiment in scientific methodology itself. The mothership hypothesis is elegant in a way that's both intellectually fascinating and vaguely terrifying. The core idea is simple. You don't send one probe to one star. That's wastefully inefficient for any civilization attempting to explore the galaxy. Instead, you send motherships on long, slow trajectories between interesting star systems. Each mothership carries dozens or hundreds or potentially thousands of smaller probes stored internally. As the mothership passes through a target system, it releases probes tailored to study specific planets or moons. The probes are expendable, relatively small, cheap to manufacture compared to the mothership itself. They conduct their observations, transmit data back, and either crash, burn up in atmospheres, or continue on their own trajectories. Meanwhile, the mothership continues to the next star system and the next, methodically mapping the galaxy over timescales measured in millions of years. From the perspective of the civilization that launched it, assuming that civilization still exists or even remembers launching it, the return on investment is extraordinary. One mothership could potentially survey thousands of star systems before malfunctioning or running out of resources, and we would never see it coming. The mothership itself would appear dark and cold, indistinguishable from a comet or asteroid until it actively started releasing probes. By then it's far too late. The probes are already in flight, already approaching their targets. Even if we detected them, we couldn't intercept with current technology. Not unless we had decades of advance warning and chose to invest enormous resources in developing and deploying intercept spacecraft. Loeb proposed a specific timeline based on orbital mechanics. If probes were released on October 29 during the hidden perihelion passage, using reverse Oberth maneuvers to slow down and capture into Earth orbit, they would arrive between November 21st and December 5th. We're talking about objects potentially the size of a shoebox, maybe even smaller, taking advantage of miniaturization technologies. Now consider Earth's space surveillance network. We can track objects down to about 10 centimeters in low Earth orbit, but that's for objects we expect to be there, objects following predictable orbits that we've cataloged. Something entering from interstellar space, something with active propulsion and maneuvering capability, could potentially evade detection quite easily. It could slip between the cracks of our surveillance net designed for passive debris, not active visitors. Would such probes make contact? Would they broadcast signals announcing their presence? Would they remain hidden, conducting observations from orbit before departing? Would they study us remotely or attempt to land and examine us up close? These are the questions that reportedly keep Loeb awake at night, because the answer determines everything about what happens next. If they represent peaceful explorers, the xenoarchaeologists, or scientific survey mission of some ancient galactic civilization, then first contact could represent the single most important moment in human history. The validation that we're not alone, that intelligence has arisen elsewhere, that the universe contains minds besides our own. It would transform philosophy, religion, science, culture, everything about how we understand our place in the cosmos. But if there's something else, if what's called the dark forest hypothesis has any validity, the idea that revealing your location to the wider galaxy is essentially a death sentence because predatory civilizations eliminate competition, then we might already be in serious danger. Detection might have already marked us for attention we desperately don't want. These are admittedly extreme scenarios, but they bracket the range of possibilities. The Galileo Project observatories will be watching continuously. 3 sites providing full sky coverage with overlapping fields of view. Any anomalies during the November-December window will be meticulously documented, analyzed, and publicly published regardless of what they show. If nothing unusual happens, if 3I/Atlas behaves exactly like a comet should and no probes materialize, then the technological hypothesis loses essentially all remaining credibility. The Loeb scale rating drops back down to 1 or 2. We file 3I/Atlas under interesting but ultimately natural and move forward. But if something does happen, if we detect objects that shouldn't exist, moving in ways that defy known physics, appearing exactly when Loeb predicted based on orbital mechanics, then we have either an unprecedented problem or an extraordinary opportunity, depending entirely on what comes next and how we respond. If you've made it this far, you're clearly invested in this mystery. You want to know what happens, what we discover, whether November brings revelation or just more data confirming what we already suspected. Here's what I need you to do. First, make absolutely certain you've subscribed to this channel, because I'll be following this story as new information emerges. Second, hit that like button if you haven't already. It genuinely helps more people discover this content. Third, and this is important, leave a comment sharing your theory. Do you think this is an unusual but natural comet? Or is there something to Loeb's concerns? I'm genuinely curious what you think based on everything you've heard so far. Now let's talk about what happened when October 29th actually arrived, because that date became the critical dividing line between speculation and observation, between prediction and reality. Solar conjunction isn't supposed to generate this much drama in the astronomical community. Most comets pass behind the sun from our perspective, disappear from view for a few days or weeks, then emerge on the other side looking predictably different. Brighter if they survive the perihelion heating intact, fragmented into multiple pieces if they didn't, dimmed and dormant if they exhausted their volatile reserves. Astronomers have observed this pattern literally hundreds of times over centuries. We know what to expect from perihelion passages. But 3I/Atlas reaching perihelion at 1.36 astronomical units on October 29th, completely hidden behind solar glare, generated uncertainty in the scientific community unlike anything most researchers had experienced. The geometry was almost cruelly perfect for creating maximum blind time. Earth and the comet positioned on opposite sides of the Sun with an angular separation that made ground-based observation physically impossible. You cannot point a telescope within 12 degrees of the Sun without destroying the instrument or permanently damaging detectors. The solar glare at that proximity overwhelms everything, making detection impossible even if the object were phenomenally bright. Even space-based telescopes like Hubble have strict solar exclusion zones built into their operational parameters. Instruments like SOHO and other coronagraphs might theoretically catch a glimpse, but 3I/Atlas was expected to be too faint, positioned too far from the solar limb to register against scattered light that's many orders of magnitude brighter. For approximately 6 weeks from early October through mid-November, humanity was essentially blind to what was happening. But perihelion represents far more than just visibility challenges. It's fundamentally about physics and the extreme conditions that occur when an icy body approaches the Sun. At 1.36 astronomical units, solar flux intensity is sufficient to vaporize virtually every volatile compound on the comet's surface. Water ice doesn't just sublimate. It transitions violently from solid to vapor. Carbon dioxide, which JWST observations had shown to be the dominant gas in the coma based on that extraordinary 8:1 ratio, transitions from solid to vapor almost instantaneously at these temperatures and radiation levels. Carbon monoxide, ammonia, methane, any supervolatile compounds trapped in the ice matrix, all of them release simultaneously in a massive outgassing event. The nucleus should essentially become a pressure cooker. Gas escaping through surface cracks and vents, dust lifted by expanding vapor clouds, the coma swelling to millions of kilometers in diameter, the tail stretching behind the comet like an enormous banner. That's what every model predicts, what every textbook describes, what every observational precedent has shown. But these models all assume we understand the composition and internal structure of 3I/Atlas. And we absolutely don't. Not really. The JWST data from August 6th revealed that shocking 8:1 ratio of carbon dioxide to water, the highest ever recorded for a comet. Most solar system comets show ratios closer to 1:1, or even water-dominated chemistry, where H2O is the primary volatile with carbon dioxide playing a secondary role. 3I/Atlas completely flips that relationship. It's fundamentally a dry ice comet with water as the secondary component. That changes everything about how perihelion behavior should manifest. Carbon dioxide ice sublimes at much lower temperatures than water ice. At 1.36 astronomical units, surface temperatures on the sunward hemisphere could easily reach 200 Kelvin or higher. That's well above the sublimation point for CO2, which begins around 150 Kelvin. But water ice requires temperatures closer to 270 Kelvin to sublimate efficiently. So we get a decoupling of volatile release, a two-stage outgassing event. First comes a massive burst of carbon dioxide exploding off the surface immediately as heating ramps up. This creates a bright, rapidly expanding coma rich in CO2. Then follows a slower, sustained release of water vapor as surface layers erode and expose deeper ice that was previously protected. The cometary behavior essentially changes phase mid-perihelion. But here's the serious complication that worries planetary scientists. If the carbon dioxide dominates initial outgassing and erupts violently enough, it could blow away the surface dust layers that normally insulate underlying water ice. Once that protective insulation is stripped away, solar radiation penetrates much deeper into the nucleus. Water sublimation suddenly accelerates. The comet could transition from a carbon dioxide-dominated system to a water-dominated system in a matter of hours or days as different layers become exposed. And we won't see any of this happen in real time. We'll only observe the aftermath when JUICE conducts its observations in November and ground-based telescopes can finally reacquire the target. We'll see the end state without witnessing the actual transformation. It's like arriving at a crime scene hours after the event. You can reconstruct what probably happened, but you miss the actual sequence of events. There's another scenario floating around in private scientific discussions that nobody wants to formally publish without more evidence. What if the comet fragments during perihelion? This isn't science fiction or wild speculation. Perihelion stress causing fragmentation is absolutely real and has been documented many times. The combination of thermal shock, internal pressure from explosive outgassing, and tidal forces from the sun's gravity field can literally tear weakly bound objects apart. We've witnessed this happen. Comet Shoemaker-Levy 9 shattered into more than 20 distinct pieces before impacting Jupiter in that spectacular 1994 event. Comet Biela split apart in the 1800s and never reformed, eventually dispersing into a meteor stream. More recently, Comet Atlas C/2019Y4 disintegrated in 2020 as it approached the Sun, simply fell apart into a cloud of debris that quickly dispersed and faded. 3I/Atlas has a rotation period of 16.16 hours, slow enough that centrifugal forces are completely negligible. Gravity should easily hold it together against rotational stress. But consider what this object has endured. It's been traveling through interstellar space for potentially billions of years. Cosmic ray bombardment continuously degrading surface materials. Temperatures cycling between near absolute zero in interstellar space and whatever warmth it absorbed during previous passages near other stars. Micrometeorite impacts creating fractures. Internal voids forming as volatiles gradually leaked away over geological timescales. The structural integrity could be severely compromised in ways we cannot possibly detect from spectroscopy or photometry alone. Those techniques tell us about surface chemistry and brightness, but they reveal essentially nothing about internal structure or mechanical strength. If fragmentation occurs, the light curve signature will be distinctive. We'd see a sudden brightening as more surface area becomes exposed to sunlight across multiple fragments. Then comes a rapid fade as those fragments disperse and the total cross-sectional area actually decreases because they're no longer gravitationally bound together. By the time JUICE observes in November, we'd see multiple condensations, separate mini-nuclei each with their own surrounding coma, strung out along the orbital path like pearls on a string. That would actually be scientifically spectacular in certain ways. Multiple samples from different depths within an interstellar comet's interior, compositional gradients laid bare, different formation layers exposed for direct spectroscopic analysis. But it would also mean we completely missed the fragmentation event itself. The moment of breakup, the forces involved, the dynamics of how the material separated, all of that would have occurred behind the sun where we couldn't document it. We'd see only the result, not the process. And in science, understanding the process often matters more than just observing the outcome. Then there's Loeb's scenario, the interpretation that treats perihelion not as a hazard to be survived, but as an opportunity to be exploited. If 3I/Atlas has any technological nature whatsoever, if it possesses any capability for propulsion or active maneuvering, perihelion represents the optimal moment to utilize it. The Oberth effect amplifies every kilogram of thrust. A relatively small propulsive burn at perihelion produces velocity changes that would require orders of magnitude more fuel if performed at aphelion in the outer solar system. If the objective is releasing probes designed to capture into planetary orbits, you'd release them at perihelion. The mathematics is completely unambiguous on this point. October 29th represents the optimal window from an orbital mechanics perspective. Loeb calculated specific parameters for what this might look like. A 10-kilogram probe equipped with a chemical rocket motor providing 500 meters per second of delta V could successfully insert into a highly elliptical Earth orbit with a periapsis around 400 kilometers altitude and apoapsis extending beyond the Moon. From that orbit, such a probe could conduct detailed studies of Earth's atmosphere, observe our oceans, monitor electromagnetic emissions across the entire radio spectrum, essentially examine anything visible from space without descending into the atmosphere itself. It could transmit collected data back to 3I/Atlas before the mothership exits the solar system beyond communication range. Or alternatively, it could remain dormant in orbit, quietly observing and recording for later retrieval by some future mission we can't even imagine. The predicted arrival window for such probes would be late November, specifically between November 21st and December 5th, depending on exact release parameters and trajectory optimization. That timeline assumes the probes use only minimal mid-course correction burns during transit. If they possess more sophisticated propulsion systems with larger fuel budgets, more advanced guidance and navigation, the arrival window potentially expands. We might see them earlier, later, or potentially miss them entirely if they actively maneuver to avoid our detection capabilities. And here's the deeply uncomfortable question that nobody wants to voice publicly. Would we even recognize such probes if they appeared? Our space surveillance network tracks cataloged objects, active satellites, space debris, spent rocket stages. We know where these objects are and can predict where they should be based on standard orbital mechanics. Something genuinely new appearing in an unexpected orbit would eventually trigger automated alerts in monitoring systems. But the response time isn't instantaneous. Processing takes time. Verification requires multiple observations. Determining orbital parameters demands tracking over hours or days. By the time we conclusively identified an anomaly, investigated its origin, ruled out prosaic explanations like previously uncatalogued debris, such a probe could have already completed its primary observational mission and potentially altered its orbit again. Loeb has specifically tasked the Galileo Project observatories with monitoring for exactly this scenario. 3 sites conducting continuous all-sky surveys simultaneously in optical wavelengths, infrared, and selected radio frequencies. Any transient event, any object moving in ways that defy standard ballistic trajectories, gets flagged for immediate analysis. During the November-December window, the detection threshold will be deliberately lowered. Yes, false positives will increase significantly, but so will overall sensitivity. If something genuinely arrives, the system should detect it. NASA and the European Space Agency have not officially commented on this particular aspect of Loeb's hypothesis. Their public focus remains squarely on the natural comet interpretation, treating 3I/Atlas as an extraordinarily interesting but ultimately explainable astronomical phenomenon. But behind closed doors, in private conversations among mission planners and senior scientists, people are absolutely paying attention. The space agencies maintain protocols for unidentified objects, not UFO contact scenarios from science fiction, but pragmatic engineering protocols for unexpected debris, untracked satellites, potential collision hazards. Those protocols can be adapted and expanded. If an object suddenly appears in Earth's orbital space with no launch history, no catalog entry, no plausible natural origin from meteoric infall, the protocols activate automatically. Tracking intensifies across military and civilian networks. Additional assets get tasked. International partners start coordinating and asking pointed questions. The machinery of space surveillance shifts into high gear whether or not anyone wants to publicly acknowledge why. October 29th was just 15 days away when these observations were being made. 3I/Atlas was already becoming invisible, progressively swallowed by solar glare as geometry placed it closer to the sun in our sky. The last productive ground-based observations occurred in late September when the comet still maintained sufficient angular separation from the sun to be safely observed. Mars orbiters, particularly the European Space Agency's ExoMars Trace Gas Orbiter, managed to capture images during the October 3rd close approach at approximately 30 million kilometers. Those Mars orbital images showed a comet behaving entirely normally by all appearances. A clearly visible coma extending thousands of kilometers, dust production rates consistent with solar heating at that distance, spectral signatures matching cometary volatile emissions. Nothing anomalous. Nothing that suggested technological systems or imminent fragmentation or any kind of crisis. Just a comet doing what comets do when solar radiation heats their surfaces and sublimes volatile ices. But perihelion represents something categorically different from what those Mars observations captured. Perihelion is where thermal stress peaks to levels experienced nowhere else in the comet's orbit. It's where internal gas pressures can exceed structural limits that held firm everywhere else. It's where decisions would get made if decisions were somehow possible. In just 15 days, 3I/Atlas would be closer to the Sun than it had been at any point in its entire multi-billion-year existence, however long that journey through interstellar space actually lasted. Surface temperatures would spike to levels hundreds of degrees higher than anything the comet experienced in the outer solar system. The outgassing rate would explode, potentially increasing by orders of magnitude, and humanity would see absolutely none of it in real time. We'd be blind during the most critical hours of this interstellar visitor's journey through our neighborhood. The only potential source of real-time data would come from heliospheric observatories, spacecraft specifically designed to monitor the Sun and its immediate environment. NASA's Parker Solar Probe, designed to study the Sun's corona by flying closer than any spacecraft in history, was unfortunately nowhere near the correct position to observe 3I/Atlas. But other solar observation platforms, including Stereo and SOHO, might manage to capture something useful. These spacecraft conduct scattered light observations, monitoring changes in brightness and structure in the Sun's immediate vicinity. If 3I/Atlas produces a major outburst during perihelion, if the coma expands rapidly enough and brightens sufficiently, the solar monitoring satellites could potentially detect changes in scattered solar radiation patterns. The data would be indirect, frustratingly low resolution compared to what dedicated comet observation missions could provide, but it would be something, at least one data point during the otherwise blind period when direct observation becomes impossible. Then comes the waiting period for JUICE observations. The spacecraft has positioned itself brilliantly for post-perihelion observations through a combination of careful mission planning and fortunate timing. Between November 2nd and November 25th, JUICE will observe with its complete suite of scientific instruments. The Janus cameras will capture high-resolution imaging. The MAGI spectrometer will analyze compositional details across multiple wavelengths. The PET particle detector will characterize the coma environment and interaction with the solar wind. The UVS ultraviolet spectrograph will identify volatile species through their emission signatures. All of these sophisticated instruments will point at 3I/Atlas as it emerges from behind the Sun, potentially still bright from perihelion heating, potentially fragmented into multiple pieces, potentially trailing a spectacular tail extending millions of kilometers, potentially doing something no one successfully predicted. The data quality should be extraordinary, providing insights into interstellar comet behavior that we've never before been able to obtain. But here's the maddening part. The data won't arrive at Earth until February 2026. JUICE is currently using its high-gain antenna as a heat shield, a necessary protective measure given its current distance from the Sun. This forces the spacecraft to rely on its medium-gain antenna for communication back to Earth. The data transmission rate through the medium-gain antenna is substantially slower than the high-gain system. Observations take absolute priority over transmission. The spacecraft will continue gathering data even if it means storing information on board for later transmission rather than sending it immediately. So the images and spectra and particle measurements get systematically stored in JUICE's onboard memory systems, queued for download when bandwidth allows and spacecraft geometry permits optimal communication. By the time we actually see what JUICE observed in November, 3I/Atlas will have already passed Venus, heading back outward toward the asteroid belt, cooling down and fading as solar radiation intensity decreases with distance. 3 months of latency, 90 days of speculation, academic argument, competing interpretations, and mounting anticipation. Did the comet survive perihelion intact? Did it fragment into pieces? Did anything genuinely unusual happen during the hidden perihelion passage that might support or refute various hypotheses? The answer technically exists right now, encoded in photons traveling from JUICE toward Earth at the speed of light, crossing the vast distance of the inner solar system. But we cannot access that information. We cannot know the truth until the data physically arrives, gets processed through analysis pipelines, and becomes released to the broader scientific community. That's the inherent cost of conducting observations at interstellar object distances using solar system spacecraft that weren't originally designed for this specific mission. We obtain unprecedented views from unique vantage points that ground-based telescopes cannot match. But we pay for those advantages in time, in waiting, in uncertainty stretched across months instead of the hours or days we've become accustomed to in the era of instant data transmission and real-time analysis. October 29th represents the critical inflection point in this entire story. Before that date, 3I/Atlas exists as a comet approaching the Sun. Unusual, certainly, raising intriguing questions, absolutely, but fundamentally explicable within known frameworks of cometary science. After that date, it becomes whatever perihelion transforms it into, a fragmented debris field scattered along its orbital path, a dramatically brightened comet sporting a massive tail, a dormant object that survived thermal stress intact but exhausted its volatile reserves and gone quiet, or something else entirely. Something requiring new categorical frameworks and new scientific terminology and new methods of interpretation that don't currently exist. The Sun hides the answer, not forever, but long enough to make the waiting feel unbearable for everyone following this unfolding story. Now let's examine what the James Webb Space Telescope revealed about 3I/Atlas's chemical composition, because this data transformed scientific understanding in ways that nobody anticipated and raised questions that still lack satisfactory answers. James Webb Space Telescope observed 3I/Atlas on August 6, 2025, when the comet was located 3.32 astronomical units from the Sun. The NIR-SPEC instrument, specifically designed to capture infrared signatures invisible to optical telescopes and human eyes, recorded spectral data spanning wavelengths from 0.6 to 5.3 micrometers. What the data revealed was not merely unusual. It represented a chemical profile that exists nowhere else in our entire observed catalog of comets spanning centuries of astronomical observation. 7.6 to 1. That's the carbon dioxide to water mixing ratio that JWST measurements revealed. To provide proper context for understanding how extraordinary this ratio actually is, consider that the next highest recorded ratio, excluding the extreme outlier Comet C/2016, R2, which represents its own category of weirdness, sits below 3 to 1. Most comets show carbon dioxide to water ratios closer to 1 to 1, with many actually being water-dominated where H2O constitutes the primary volatile component. 3I/Atlas isn't just rich in carbon dioxide. It's absolutely dominated by dry ice to a degree that fundamentally challenges our models of how comets form and what conditions produce specific chemical compositions. Martin Cordiner from NASA's Goddard Space Flight Center led the analysis team that processed this data. The research paper uploaded to the AR-14 preprint server in late August laid out the observations in meticulous detail. The coma shows enhanced outgassing specifically on the sunward side, exactly as expected from straightforward solar heating physics. Water is definitely present in detectable quantities. Carbon monoxide appears in the spectral signatures. Carbonyl sulfide shows up in tentative detections that require further confirmation. Water ice signatures appear clearly in the spectral data. Dust scattering creates visible signals in the near-infrared wavelengths. All of this fits perfectly normal comet behavior. All of it slots comfortably into existing frameworks for understanding how icy bodies interact with solar radiation. Except for that ratio. The 7.6 to 1 carbon dioxide to water ratio sits 4.5 sigma above the established trend line for both long-period comets and Jupiter family comets observed at similar heliocentric distances. In statistical terminology, sigma measures standard deviation from the mean. 1 sigma represents normal, expected variation. 2 sigma is notable enough to warrant attention. 3 sigma is genuinely rare, occurring in less than 1% of random samples. 4.5 sigma is the kind of deviation that makes statisticians seriously question whether your comparison sample is even relevant anymore. When you encounter deviations this extreme, you begin wondering whether you're looking at an outlier from a known population or actually observing a member of a completely different population that you're incorrectly trying to fit into familiar categories. Maybe 3I/Atlas isn't an outlier at all. Maybe it's a completely normal example from a population we've never sampled before, and we're making a category error by comparing it to solar system comets. The carbon isotope ratios provide another crucial piece of this chemical puzzle. JWST detected both carbon-12 and carbon-13 in the coma emissions, allowing researchers to calculate the ratio between these isotopes. The measured ratio sits comfortably within the range found on Earth and throughout our solar system. That strongly suggests the carbon formed in a similar stellar environment, not in a population 3-star from the very early universe where metallicity was essentially zero, not in a carbon star enriched with unusual nuclear synthesis products, but just normal carbon produced through standard stellar nucleosynthesis in a star not dramatically different from our Sun. But while the isotope ratios appear normal, the sheer abundance of carbon dioxide relative to water tells a profoundly different story about where and how this ice originally formed billions of years ago. There are 2 primary competing explanations for this extraordinary ratio, and both frameworks have significant theoretical problems that researchers are still wrestling with. The first explanation involves radiation processing over immense timescales. If 3I/Atlas formed in a protoplanetary disk exposed to intense ultraviolet radiation from a hot, young star, or if it spent billions of years traveling through the interstellar medium being continuously bombarded by high-energy cosmic rays, the water ice could have been preferentially destroyed through photodissociation. Water molecules are substantially easier to break apart than carbon dioxide molecules due to their chemical bonding structure. High-energy photons and energetic particles strike the ice, cleaving the hydrogen-oxygen bonds, and the freed hydrogen atoms escape into space because hydrogen is so extraordinarily light that even weak gravitational fields cannot retain it. The liberated oxygen atoms can then recombine with available carbon to form additional carbon dioxide molecules, progressively enriching the CO2 concentration. Over geological timescales spanning billions of years, an initially water-rich comet could theoretically become progressively carbon dioxide-rich through sheer cumulative radiation damage and preferential hydrogen loss. The fundamental problem with this radiation processing explanation is quantitative. To shift a comet's composition from roughly equal parts water and carbon dioxide to an 8:1 ratio favoring CO2 requires truly extreme radiation exposure sustained over extreme timescales. We're talking about billions of years in the interstellar medium with essentially no protective shielding whatsoever. That's certainly plausible for 3I/Atlas given its potential age if it formed during the early galaxy's thick disk era. But this scenario also requires that water ice remained exposed on the surface the entire time. If the comet has any protective dust mantle, any internal layered structure that shields deeper ice from radiation, the processing efficiency drops dramatically. You develop a compositional gradient with heavily processed CO2, enriched ice on the surface, and relatively pristine, water-rich ice in the interior. When the comet becomes active and starts shedding surface layers through sublimation and dust loss, the ratio should change progressively as deeper material becomes exposed. We haven't observed that change yet. The ratio has remained remarkably consistent between the August JWST observations and earlier SphereX infrared data from mid-August. The second major explanation involves the original formation location within a protoplanetary disk. Carbon dioxide has a significantly lower condensation temperature than water ice. In any protoplanetary disk, there exists a boundary called the CO2 ice line or snow line. Inside that boundary closer to the star, carbon dioxide remains gaseous because temperatures are too high for it to condense. Outside that line in the colder outer disk regions, CO2 condenses into solid ice that can be incorporated into forming comets and planets. The water ice line sits at a different location, generally closer to the star, because water has a higher condensation temperature. If 3I/Atlas formed beyond the CO2 ice line in a protoplanetary disk, where carbon was unusually abundant relative to oxygen, perhaps due to the host star's particular metallicity or specific disk chemistry, it could naturally incorporate substantially more carbon dioxide than water during its initial accretion. The ratio gets frozen into the comet's fundamental composition from day one of its formation. This formation location explanation requires fairly specific and potentially fine-tuned conditions. You need a protoplanetary disk with an unusually high carbon-to-oxygen ratio, or alternatively a disk where the temperature gradient and chemical distribution place the forming comet in a zone exceptionally rich in CO2 ice, but simultaneously depleted in water ice. Both scenarios are physically possible. Stellar metallicity does vary significantly between different star systems. Disk structure and chemistry definitely vary based on numerous factors. But naturally producing an 8:1 CO2 to water ratio isn't trivial. It requires conditions that should be uncommon, though not impossible. SphereX observations from mid-August provide important supporting evidence for understanding this chemical anomaly. The space-based infrared telescope detected a massive carbon dioxide cloud extending at least 348,000 kilometers from the nucleus, more than 200,000 miles, nearly the distance from Earth to the Moon. Notably, there was no corresponding water cloud detected at similar spatial scales. The CO2 is escaping faster, traveling farther from the nucleus, absolutely dominating the observable coma structure. Meanwhile, water production rates remained frustratingly below SphereX's detection limits, with observational upper bounds around 4.5 kilograms per second. That's approximately an order of magnitude below Swift Observatory's earlier detection of 40 kilograms per second, which itself was questionable given the observational distance and the indirect methodology of detecting hydroxyl radicals rather than water molecules directly. This apparent discrepancy between different telescopes' water measurements tells us something important about the challenges of observational astronomy. Water detection is genuinely difficult, requiring specific wavelengths and specific instrument capabilities. Swift detected hydroxyl groups, the breakdown products created when ultraviolet radiation tears apart water molecules, not intact H2O. Sphere X looked for characteristic water emission lines in the infrared spectrum and came up essentially empty. JWST found water clearly present, but at substantially lower abundance than carbon dioxide. Each telescope essentially sees a different piece of the overall puzzle. Reconciling these disparate observations requires making assumptions about photochemistry rates, about how quickly molecules break down under solar radiation, about the spatial distribution of different species throughout the coma. None of those assumptions are particularly well constrained for an interstellar comet with genuinely unknown composition from an alien star system. One fascinating detail buried in the JWST data stands out to specialists. The water emission signature at 2.7 micrometers shows clear spatial structure rather than being uniformly distributed throughout the coma. There are distinct bright regions and dim regions, strongly suggesting localized sources, possibly jets erupting from specific active areas, or perhaps pockets of water-rich ice mixed into a predominantly carbon dioxide matrix. When those isolated water-rich pockets become exposed to direct sunlight, they release water in concentrated bursts rather than steady, uniform sublimation across the entire surface. The result appears patchy and non-uniform in JWST's spatial spectral maps. In contrast, the carbon dioxide emission at 4.3 micrometers appears much smoother and more evenly distributed spatially, entirely consistent with widespread sublimation occurring across the entire sunward hemisphere. That spatial difference has profound implications for understanding the comet's internal structure and composition. If 3I/Atlas were compositionally homogeneous, just carbon dioxide ice throughout with no significant variation, the outgassing pattern should be relatively uniform across the sunlit surface. The fact that water shows distinctly localized emissions strongly suggests compositional heterogeneity. We're likely seeing chunks or distinct layers or isolated pockets of different composition distributed throughout the nucleus structure. This heterogeneity might represent the comet's original formation structure, with different materials accreting at different times or from different regions of its birth protoplanetary disk. Alternatively, it could result from billions of years of evolution in interstellar space, with radiation processing, thermal cycling, and cosmic ray bombardment creating a complex, layered internal structure that bears little resemblance to how the object looked when it first formed. If you're still watching at this point, you're clearly deeply invested in understanding what we're learning from this remarkable object. I want you to do something specific right now. Leave a comment sharing which aspect of 3I/Atlas fascinates you most. Is it the chemical composition anomaly? The possibility of technological origin? The trajectory that brings it past multiple planets? The mystery of what's happening right now during its hidden perihelion passage? Your engagement helps this content reach more people, and these are questions that deserve the widest possible audience. Also, make absolutely certain you've subscribed and enabled notifications, because as new information emerges over the coming months, I'll be creating follow-up content analyzing what we discover. Now we need to discuss what happens after perihelion, because that post-perihelion period will determine whether 3I/Atlas remains an interesting anomaly or becomes something that fundamentally challenges our understanding of what travels between the stars. The geometry of solar conjunction means that 3I/Atlas will be unobservable from Earth from approximately October 1st through November 9th, 2025, a blackout period of more than 5 weeks encompassing the critical perihelion passage. During this time, the comet will make its closest approach to the Sun on October 29th at approximately 1.36 astronomical units, just inside Mars's orbital distance. Solar radiation intensity at that distance is roughly half what Earth experiences, still more than sufficient to drive intense cometary activity if volatile ices remain present in substantial quantities. Current predictions suggest the comet could brighten significantly during perihelion, potentially reaching apparent magnitude 11 or even 10 if outgassing rates increase as dramatically as models suggest they should. At magnitude 11, the comet would become theoretically visible through good amateur telescopes under dark sky conditions, though the small angular separation from the Sun makes actual observation extremely challenging and potentially dangerous without proper equipment and safety precautions. Mars orbiters will have the best observational opportunity during the perihelion period. From Mars's vantage point, 3I/Atlas will achieve an apparent magnitude around 11, well within the detection capabilities of spacecraft like the European Space Agency's Mars Express and ExoMars Trace Gas Orbiter. These orbiters weren't designed for comet observation. Their primary mission involves studying Mars's surface and atmosphere, but they've demonstrated remarkable flexibility in targeting astronomical opportunities. The ExoMars CASIS camera system successfully imaged 3I/Atlas during the early October close approach, despite the comet being approximately 50,000 times fainter than the Martian surface features the instrument was designed to photograph. By using extended 5-second exposures and careful pointing, the camera captured clear images showing the coma structure. If perihelion activity increases as expected, the comet should actually become easier to observe from Mars orbit, potentially allowing for detailed time series observations documenting how the outgassing evolves over hours and days. Those Mars orbital observations could provide the only real-time view of perihelion behavior, filling in the critical gap when Earth-based observation becomes impossible. The data from Mars orbiters won't have the spectroscopic sophistication of JWST or the spatial resolution of Hubble, but it will show whether the comet survives intact, whether it fragments, whether the coma expands dramatically, whether a prominent tail develops. All the basic observational metrics that indicate how perihelion stress affects the object. When 3I/Atlas finally emerges from solar conjunction in early to mid-November, becoming visible from Earth again in the pre-dawn sky, the scientific community will be watching with unprecedented intensity. Ground-based telescopes across the world will immediately target the comet, eager to document its post-perihelion state. Has it brightened? Has the coma expanded? Is there evidence of fragmentation? Has the dust-to-gas ratio changed? Are there new spectral features indicating different volatile species becoming active? The JUICE spacecraft observations between November 2nd and 25th will provide the highest quality data during this crucial post-perihelion period. Multiple instruments operating simultaneously will build a comprehensive picture of the comet's physical state, chemical composition, and activity level. The JANUS camera system will capture high-resolution images showing coma structure, potential jets, dust distribution, and any evidence of nucleus fragmentation. The MAGI spectrometer will analyze composition across near-infrared and visible wavelengths, identifying which volatile species are actively sublimating and in what relative abundances. The particle detectors will characterize the coma environment, measuring the density and velocity distribution of gas and dust particles. The ultraviolet spectrograph will target specific volatile emissions that are particularly diagnostic of composition and activity level. All of this data will be systematically collected, time-stamped, and stored aboard JUICE for later transmission when the spacecraft's communication geometry permits efficient downlink. But again, that data won't reach Earth until February 2026 at the earliest. The 3-month delay between observation and data availability creates enormous frustration within the scientific community, but it's an unavoidable consequence of the spacecraft's current operational status and the limitations of deep space communication bandwidth. In the interim between mid-November 2025 and February 2026, we'll have only ground-based observations to work with. Those observations will certainly be valuable, numerous professional observatories and advanced amateur astronomers will be tracking the comet continuously. But ground-based observation has inherent limitations compared to space-based platforms. Earth's atmosphere distorts incoming light, limiting spatial resolution. Terrestrial weather creates observing gaps. The need to observe during twilight when the comet sits low on the horizon adds atmospheric extinction that dims the target and reduces data quality. Nevertheless, ground-based observers will provide crucial monitoring showing how 3I/Atlas evolves in the weeks and months following perihelion. The comet should gradually fade as it moves away from the Sun and activity levels naturally decline. By December 2025, the comet is predicted to fade below apparent magnitude 12, requiring increasingly large telescopes to observe effectively. By January 2026, it will likely be magnitude 13 or fainter, accessible only to professional facilities and the most advanced amateur setups. The expected trajectory carries 3I/Atlas through the constellation Virgo in December 2025, passing into Leo by early 2026. Its high speed relative to the Sun, approximately 58 kilometers per second hyperbolic excess velocity, means it will visibly move against the background stars quite rapidly. Observers will be able to track its motion over days and weeks, watching it race through our inner solar system before departing forever back into interstellar space. That phrase, forever, carries weight that's worth pausing to fully appreciate. Unlike periodic comets that return at regular intervals, unlike asteroids that remain gravitationally bound to the Sun, 3I/Atlas is genuinely visiting. After this single passage, it will depart our solar system and continue traveling through the galaxy indefinitely. In March 2026, it will pass through Jupiter's orbital region, receiving a gravitational assist that actually increases its velocity relative to the Sun. From that point onward, nothing can prevent its departure. Within a few years, 3I/Atlas will be farther from the Sun than Neptune, entering the Kuiper Belt region. Within a decade, it will pass beyond the heliopause into true interstellar space. Within a few centuries, it will be light years away, coursing between the stars once again, carrying with it all the information encoded in its composition and structure about its distant point of origin. This finality creates urgency unlike anything in typical astronomical research. Usually, if observations are inconclusive or insufficient, researchers can propose follow-up studies, wait for better technology, plan return missions. With 3I/Atlas, we get one chance. Every missed observation is permanently lost. Every question we fail to answer now might remain forever unanswered. That reality drives the intensity of effort and the careful coordination among observing teams around the world. The spacecraft that has the best opportunity for extended close-range observation would be JUICE, but that mission has other priorities. JUICE's primary targets are Jupiter and its large icy moons, Europa, Ganymede, and Callisto. The spacecraft is currently in a complex series of gravitational assist maneuvers using Earth, the Moon, and Venus to progressively alter its trajectory for eventual Jupiter arrival in July 2031. The November 2025 observations of 3I/Atlas represent a fortunate alignment that mission planners are exploiting, but they cannot fundamentally alter JUICE's trajectory to conduct extended comet observation without jeopardizing the primary mission. So we're left with this situation: the most scientifically interesting interstellar object ever observed, displaying chemical composition anomalies that challenge formation theories, following an improbable trajectory past multiple planets, reaching peak activity during a period when Earth-based observation is impossible, and departing forever before we can mount any kind of dedicated close-range mission. It's simultaneously exhilarating and frustrating, the ultimate case study in astronomical serendipity combined with logistical limitations. Abraham Loeb has argued that this situation demonstrates exactly why we need dedicated rapid response spacecraft capability specifically designed for interstellar object encounters. By the time we detect these visitors, they're already deep in the inner solar system. By the time we fully characterize them and understand what questions need answering, they're already departing. A prepositioned rapid response spacecraft, perhaps stationed at the Earth-Sun L1 Lagrange point, could theoretically launch intercept trajectories within days of a new interstellar object detection. Such a spacecraft wouldn't need to be enormous. A relatively small probe with high delta-V capability, carrying a basic suite of cameras, spectrometers, and particle detectors, could conduct valuable close flybys that answer questions ground-based observation cannot address. The technology exists. The challenge is purely organizational and financial. Convincing space agencies that the scientific return justifies the investment when we might wait years or decades between interstellar object detections. The recent discovery rate suggests we're detecting roughly one interstellar object per 2 to 3 years, though this rate is heavily biased by our improving detection capabilities. As survey telescopes become more powerful and more numerous, the detection rate will almost certainly increase. The Vera C. Rubin Observatory, which just began science operations in 2025, is expected to discover substantially more interstellar objects than any previous survey. Within a decade, we might be detecting multiple interstellar visitors annually, each one potentially answering different questions about galactic populations of small bodies. But for now, 3I/Atlas remains the focus of attention, the object currently teaching us the most about what exists in interstellar space and what arrives in our cosmic neighborhood. As it completes its hidden perihelion passage and emerges back into observable space in mid-November, the entire astronomical community will be watching intently, hoping for answers but prepared for new mysteries. Because that's ultimately what 3I/Atlas represents, not just an object to study, but a profound reminder of how much we don't know about the universe beyond our immediate solar system. Every time we think we understand comet composition and behavior, an object like this appears and forces us to expand our frameworks. Every time we develop confident predictions, an interstellar visitor arrives that doesn't follow the script. This pattern suggests something important about the nature of scientific knowledge itself. Our understanding is built on the sample we've been able to observe, primarily solar system objects formed from the same protoplanetary disk that created Earth and the other planets. That sample, however large it seems with thousands of cataloged comets and asteroids, represents a tiny fraction of the diversity that exists in the galaxy. Different star systems formed under different conditions, different metallicities, different radiation environments, different giant planet configurations that scattered objects into different reservoirs. The interstellar objects we're now beginning to detect carry information from those other systems, those other formation environments. Each one arrives like a geological core sample from an unreachable continent, packed with data about conditions we cannot directly observe. 3I/Atlas, with its extreme carbon dioxide enrichment, tells us about a formation environment substantially different from our own. It suggests disk conditions that either started with unusual chemistry or experienced radiation processing that dramatically altered initial composition. Understanding these differences matters for more than just comet science. It informs our understanding of planet formation, of how planetary systems develop and evolve, of what conditions produce habitable worlds versus lifeless frozen bodies. The chemistry we see in 3I/Atlas existed in a protoplanetary disk that might have also formed planets. If so, those planets formed in a carbon dioxide-rich environment quite different from Earth's water-rich formation zone. Would such planets develop similar geology, similar atmospheres? Could life emerge under those different chemical starting conditions? These questions extend far beyond the immediate puzzle of one unusual comet. They touch fundamental questions about our place in the universe, about whether Earth-like conditions are typical or exceptional, about whether the chemistry that led to life here represents a common galactic pattern or a rare fortunate accident. Right now, in mid-October 2025, 3I/Atlas is approaching the climax of its journey through our solar system. Within 2 weeks, it will reach perihelion, experiencing solar radiation intensities it hasn't felt in billions of years of interstellar wandering, if ever. The volatile ices that have survived the journey are about to experience their greatest test. The outcome will tell us whether this object is structurally robust or fragile, whether its composition allows it to survive thermal stress, or whether it will shatter and disperse. And we won't see it happen. We'll only see the result, the aftermath, what emerges in November when observation becomes possible again. That enforced waiting, that gap in observation during the most critical period, adds dramatic tension to an already fascinating scientific story. It's a reminder that despite all our technological sophistication, despite our fleet of spacecraft and powerful telescopes, nature still keeps secrets. The universe still has the power to surprise us, to operate beyond our direct observation, to unfold according to physical laws we can only imperfectly predict. When the answer finally arrives, when JUICE's detailed observations reach Earth in February 2026, showing us what perihelion did to this interstellar traveler, we'll gain crucial insights. We'll learn whether current comet models apply to interstellar objects or whether we need new frameworks. We'll discover whether Loeb's technological hypothesis finds any supporting evidence or gets definitively ruled out. We'll understand better what happens when a carbon dioxide-dominated comet experiences intense solar radiation. But even as those answers arrive, they'll inevitably generate new questions. That's the essential pattern of scientific progress, each answer illuminating new mysteries, each solved puzzle revealing deeper complexity beneath. 3I/Atlas won't provide final answers about interstellar objects. It will simply add crucial data points, expand our understanding incrementally, and prepare us better for future visitors that will arrive with their own unique characteristics and their own challenging questions. For now, all we can do is watch and wait. The comet continues its approach, carrying its mysteries with it, heading toward a solar encounter we cannot observe, preparing to teach us lessons we haven't yet learned. And in November, when it emerges back into view, potentially transformed by perihelion, potentially fragmented, potentially doing something unexpected, we'll be ready with our telescopes and instruments and questions. This is the reality of astronomical discovery in the 21st century. Spectacular capability combined with humbling limitations, powerful insights alongside frustrating gaps in knowledge, extraordinary precision observation punctuated by periods of enforced blindness. We've never been better equipped to study the universe. We've never been more aware of how much remains beyond our current understanding. 3I/Atlas embodies this paradox perfectly. An object detected millions of kilometers away, analyzed spectroscopically to determine its chemical composition, tracked precisely through its trajectory, yet fundamentally mysterious in its origin, uncertain in its fate, teaching us as much about the limits of knowledge as about interstellar space itself. If you've stayed with this journey through the mystery and science of 3I/Atlas all the way to this point, you're part of a community that values deep understanding over superficial answers, that appreciates the process of scientific discovery even when definitive conclusions remain elusive. That makes you exactly the kind of person who should be sharing this content. Hit that share button and send this to someone who appreciates genuine intellectual exploration. Leave a comment. Specifically, I want you to write Atlas if you watch this entire presentation, because I'm genuinely curious how many people complete this deep dive into the science. And most importantly, Make sure you're subscribed with notifications enabled, because as November arrives and new observations emerge, as JUICE data eventually reaches Earth in February, I'll be creating follow-up content analyzing what we've learned. This story is far from over. We're living through a pivotal moment in our understanding of what travels between the stars, and you're here witnessing it in real time. The next video that should be appearing on your screen right now continues exploring mysteries of space and scientific discoveries that challenge our understanding. Click through and continue this journey of exploration. For everyone who made it this far, thank you for your intellectual curiosity, your patience with complex science, and your willingness to embrace uncertainty while waiting for answers. That's the essence of scientific thinking, and the world needs more people like you. Until next time, keep looking up, keep asking questions, and keep wondering about what else might be out there in the vast darkness between the stars, heading our way right now, carrying mysteries we haven't even imagined yet.